So let's go to read a few lines of this book. For setting up an interesting application, what I need, what is requested? Usability, scalability, portability, and versatility. The system, my application, must be robust, a good cost, a reasonable cost, maintenance, and user interface. These are things that are nowadays are standard, okay? Biological systems are diverse and very versatile. I am a diver is amazing what the different shapes of fishes and animals that you can find is amazing, okay, down water. And guys, which are the elements who are building the biological systems? Very few. Carbon, hydrogen, sulfur, something, not too much. So very few elements, okay? So the bricks are minimal. And if we go a little bit higher, again, we have building blocks, DNA, RNA, okay? But proteins, they can be sensors, they can build our skeleton. So the same building blocks are used in different ways. And hopefully they are robust. We are a proof. Okay. Let's see, a fly again. Let's go back again to examine what a fly does. This fly, that is the Drosophila odorant receptors, okay? It has, this fly, it's a fruit fly, okay? It's a fruit fly, standard fruit fly. It has 57 genes that code the possibility to detect this specific flower or something that is needed for living. The first thing, each gene encodes 7 transmembrane proteins built of 38 amino acids. So it has an architectural organization. It is an architecture. I have my biomolecules, my DNA, but I have my protein, I have my genes, I have each gene. So it is an architecture. Then, when my system, my genes detect the odor that I'm looking for, they pass the message to the neurons, to the small brain, but a brain, okay? So I have communication. There is a communication system. Then everything goes to the sensory center in the brain. And these centers, they elaborate and they say, ah, this is the odor you are looking for. They have an artificial intelligence algorithm, let's call it like this, that takes the information from all the genes and they say, okay, this is the odor of this is the odor of something that I don't like, let's go out. So I have the elaboration and I have also a memory, because if I detect that this is the odor, I have a memory to know which is an associative memory. I have some memory for remembering that this is the odor I want. So guys, what is a device that is an architecture? It communicates, it elaborates things, and has a memory. What are we looking for? We are talking of an electronic system. So the message of today, and I will now start showing you some example, is, guys, the biological system are finally a computing system. What we have in mind as computing system. But do we have to mimic the brain? In my opinion, no. It's an opinion. The other people are thinking differently. But the brain, it works well. It was designed a long time ago So it is a good efficiency. It's not needed to rebuild it. But yes, we have to take ideas. We have to take solutions from brain and what is around the brain. And so it is time to start thinking to a biomolecular computer, using molecular biology. The first molecule that we start to examine are the DNA and the amino acids. Again, Yuval Garini gave you a fantastic introduction, even much better than mine, because he's the expert, I'm not. So here, well, in my standard presentation, I prepared a sort of armoire where we have our basic knowledges that we can recover in terms of nucleotides and amino acid. Just I go quickly goes. You remember, it is the double helix. From the double helix, we have a pairing, G with T, G with C, T with A, okay? This is the key, remember it. And then from the DNA, we can build the proteins inside genes, the genetic information. There are chromosomes with a logic structure. I pass quickly because I want to recover you quickly this concept because I use them later. We have our human genome. Yuval did a fantastic presentation of a system of messenger RNA and everything. So you see, this is a fantastic machine. It is a fantastic machine. Consuming very, very low amount of power. We can survive with an apple, okay? Not for the full life, but with very few kilocalories, okay? So we move to proteins, and then putting together amino acid and proteins, we can build proteins that have many different ways of applications, okay? And they can change shape, they change behavior depending on the environment. They are perfect sensors too, not only structure molecules. So they can denature. There are many roles of a protein. You see, mechanical structure, enzymes. I will talk specifically of enzymes now. Balance of fluids, transport, energy. They can also bring energy. So the same brick protein can be used in several different ways. And we have the 4 different structures of proteins. What I want to highlight you here, it is how much is powerful, how it is versatile, okay? Recalling what I mentioned before. But all these concepts were already done by Yuval. So we have okay, another important point that I put to this slide. We have metalloproteins, because again, I'm talking of electrical, nanoelectronic. So to have something that has some metal, some electrons to exchange, it is useful for using it. So to have metalloproteins is another interesting issue. So coming back down to our main track, let's go also what Evgeny wrote in his book, and so let's again extract some interesting information, okay? Now I hope that after that I started introducing you, that it's clear that our biomolecular system, they are processing, logic operation, they can make computation, and I will show you some examples. So they can be the hardware for doing this unconventional computing, okay? And we will merge physics and chemicals together. An important topic I did not touch yet, parallelism. We are intrinsically parallel. So, you see, you have 10 to 23 molecules doing computations in parallel. Wow. So, we are completely changing the order of magnitude of transistors, equivalent transistors we have in our hands. And they are intrinsically working in parallel. Fantastic. And they deal, it was written nonlinear, they deal with nonlinear behaviors. We are always terrified about nonlinearities. Nature is nonlinear by definition. So again, we can use this. And for this, let's see the first example. The first example was done, and it is presented in the Evgeny book, where the people start building gates, AND gates, half-adder, and all these devices, of course, must be reversible and reconfigurable. So if I have a device, when I use it, I have to reuse it again. And with biological system, we have to do something that we don't do in standard electronics, but we will see. So we must reset. What we start today together is to look how I can build a flip-flop using some organic, let's start with organic, simpler molecules, and after we will step forward up to reach cells. For a flip-flop, with paper injects, it is a few years ago, and it is based on this molecule that it is this complex, organic complex, that have a behavior in this case. So when I illuminate my complex with a visible light, it goes to a status named 1E that is not fluorescent. If I illuminate my molecule with ultraviolet, it becomes in the status 1C, and 1C has a fluorescence about 644 nanometers. How I can exploit this molecule for building a flip-flop? Guys, with a complex system, okay, we will reach more interesting application, but the path I want to do with you is step by step, okay? But let's see. Can I make a flip-flop of it? Let's see. I can take a laser, infrared laser, that it is my data input. Then I take another laser, again infrared, but I had a second harmonic generator that from the infrared light extracted 532 nanometer visible light. And this visible light for me is the clock on my flip-flop. Let's see what happens. Before I insert a third harmonic generating crystal here that merges and take all the different lights entering and mixing them together, because thanks to this, remember, only if I have the infrared and the visible light together, it is generated out an ultraviolet light. Okay, so how this system works? Things in this. Data input. So I give infrared light to my molecule. I put down here, to remember, with infrared light, nothing happens. So it's the data, like in a flip-flop, if I have the data, but without the clock, nothing happens. I switch on my laser. I give the clock input. I have now the infrared light plus the visible light. It is generated the ultraviolet, so the ultraviolet stimulates my molecule that becomes fluorescent. The input, so if I have the infrared, it is 1. So I have 1 is input, I have the clock arrived, in output I stimulate a fluorescence, and so fluorescence means 1. So guys, I use this example because it's the first time that we start thinking to a digital device, not using anymore amplitudes in voltage. We are using input. Input is the light of a laser. On means 1, off means 0. I have light means 1, I don't light, it means 0. Exit, output. I have light, fluorescence is 1, I don't have light is 0. So we are putting in relations to 1 and 0 different things that up to now we did with electrons or voltages, okay? But if the clock arrives, so the visible light arrives, and in parallel I don't have the infrared light, what happens? On the top of my molecule, just the visible light arrives, because the ultraviolet is not generated. I don't have the infrared. And so I stimulate my molecule. My molecule could be in any state. It goes to zero. It goes to the not fluorescent state. I did a flip-flop. And it has a memory. Because when it changes state, it stays there, the molecule. Do you got it? Did you got it? Yes? It's a flip-flop. Using very strange things, yes. Light, biomolecules, fluorescence, but it works. Performances. Okay. Generally, the change of state, it is less than 10 picoseconds. Wow, I like it. 10 picoseconds. But putting all together, I need 45 seconds to have the results. This is not a bad news. But guys, think of the first transistor in the 50s. Was a crap, was not working, of course. So we are at the start, but it works. Another important thing that is not have to be forgotten is the reversibility. And the process is reversible. The molecule can go up and down, fluorescent, not fluorescent. You see, with, of course, some errors, some noise, but it can go up and down as soon as I want, for a long time. Okay? So, good. Did I start to convince you a little bit? I hope yes. Now, let's move to another system. Another system, it was published in Nature, not the last paper, journal, okay? So means that as a meaning. Few years ago, we are talking of 94, so a long time ago, but people started thinking about this application a long time ago. And this is a switchable chemically and electrochemical molecular shuttle based on these complexes. This is the, I'm not a chemist, please don't ask me to go in details. We don't need to go in details of a molecule, but what is interesting is that this is a sort of chain that in the plot is schematized with a sort of cylinder and a structure that is a sort of ring, okay? And what happens to these two molecules? If they do not have any base, B stands for base or acid, H+, so if I don't have anything, they are connected. So the ring is around the cylinder. If the ring is around the cylinder, I do not have fluorescence. Let's talk again. The output is fluorescence. The input is no more light. The input is base or acid solution. Again, we are adding more things. Good, because we have the technology. I demonstrated it. You can use it. So, or if I have both, so if I have in solution some bases and some acids, again, the situation is that the ring stays around the cylinder, and so I don't have fluorescence. But if I have just bases, only bases like this, or only acids, the ring disconnects from the cylinder. Good. I have fluorescence if I have B. I have fluorescence if I have H+, so I have acid. I do not have fluorescence if I have no input, 0, or both input. 1, 0, 1. 0, 1, 1. 0, 0 or 1, 1 is 0. What it means? An XOR. I did an XOR gate. Okay? Strange, but it works. So, sorry, the inputs. Now we are starting or really exploiting several physics, several chemicals for having our inputs. Same for the outputs, fluorescence, pH, and we can have electrochemical, so current, we can jump in current again, but from electrochemical systems. In fact, we can talk of our hardware in terms of making electrodes. We need them, nanowires that can change proportionally to pH conductivity. We can make single molecule transistors. So you see, I can use electronics, electrodes, transistors for setting up the system, but I'm not using for the computation the electronic system. Of course, as I already mentioned, because I'm really convinced of this, that is not the way of copying and replicating the things. The idea is to find novel approaches to the hardware and computing power, taking inspiration from the nature and from this system. Then, and after we do a small break, I can have two main approaches, the chemical approach or the biomolecular approach. In chemical approach, well, the chemical approach is more difficult to prepare, it is difficult to scaling up down, and well, in terms of chemistry, maybe it is a little bit more complex. In terms of biomolecule, the complexity is inside the molecule. The molecule itself is complex. I don't have to build it like in chemical. So DNA, proteins, full cells are already complex systems. Simply, I have to use them in the right way. So the cells, they do the DNA intrinsically automata operations. So they can use for taking decisions, okay? And also robotic functions, they make them intrinsically. And of course, in literature, I'll mention several different examples. I don't want to list them in the way, but biomedical, of course, diagnostic, I will show you some examples. Homeland security, also I will show you one example in homeland security. Personalized medicine. Personalized medicine is one of the important issues nowadays in which pharma companies are investing. And so, you know, if I use directly the cells, I can use your own cells. I can take decisions not based on something standard. I can take decisions on your own cells. Fantastic.